You know, when people talk about going to the moon, they make it sound like it's just another trip. Like you're booking a flight to another country. But the reality is so much more complicated than that. And today, we're going to break down exactly why landing on the moon is one of the most difficult things humans have ever attempted to do. And look, I'm not going to bore you with a bunch of complicated science terms or make this feel like a college lecture. I'm going to explain this in a way that actually makes sense. Because once you understand what's really involved in getting to the moon and landing on it, you'll realize just how incredible it is we ever managed to do it at all. But before we get into all of that, if you want to see more content like this where we break down complex topics and make them actually understandable, go ahead and hit that subscribe button right now. We put out videos like this every single week, and trust me, you don't want to miss what's coming next. Alright, so let's start with the most basic problem. The moon is really far away. And I know that sounds obvious, but most people don't actually understand just how far it is. The moon is sitting about 240,000 miles away from Earth. To put that in perspective, if you could drive a car straight up into space at highway speed, it would take you about 6 months of non-stop driving to reach the moon. 6 months. In a car. Going 60 miles per hour. Non-stop. But obviously, we can't drive to the moon. We have to use rockets. And even with rockets that are traveling at thousands of miles per hour, it still takes about 3 days to get there. 3 full days of traveling through empty space. And during those 3 days, everything has to work perfectly. Because if anything goes wrong, you're 250,000 miles away from any kind of help. Now, getting to the moon is hard enough, but landing on it, that's a completely different challenge. And this is where things get really interesting, because the moon doesn't have an atmosphere like Earth does, and that changes everything. See, when you land an airplane on Earth, you can use air resistance to slow down. The wings catch the air, the engines can push against the air, and you have all these tools to help you control your descent. But the moon doesn't have air. There's no atmosphere, which means there's nothing to slow you down except your own rocket engines. Imagine driving down a highway at 60,000 miles per hour, and the only way to stop is by pointing your car backwards and firing a rocket engine. That's basically what landing on the moon is like. You're falling towards this giant rock at incredible speeds, and the only thing stopping you from crashing is a rocket engine pointing down, fighting against your momentum. And here's the thing that makes it even harder. You can't just blast the engine at full power the whole way down, because rocket fuel is heavy, really heavy. And you only have so much of it. If you use too much fuel trying to slow down, you won't have enough left to actually land. Oh, but if you don't use enough fuel, you'll crash into the surface at thousands of miles per hour. So you have to find this perfect balance. You have to slow down at exactly the right rate, using exactly the right amount of fuel, while also making sure you're landing in a safe spot. And you're doing all of this while traveling faster than any human has ever traveled before. Let's talk about the fuel situation more, because this is crucial. A rocket landing on the moon is carrying all the fuel it needs for the entire landing. There are no gas stations in space. There's no way to refuel. Every single drop of fuel had to be brought from Earth, which means it had to be lifted through Earth's atmosphere first. And lifting fuel through Earth's atmosphere requires even more fuel. It's like this never-ending cycle where you need fuel to carry fuel to carry fuel. This is why moon rockets are so massive. The Saturn V rocket that took astronauts to the moon was 360 feet tall. That's taller than a 30-story building, and most of that height was just fuel tanks. The actual crew capsule where the astronauts sat was tiny compared to the rest of the rocket, because most of the rocket's job was just carrying enough fuel to get there and back. Now let's talk about navigation. When you're driving a car, you can see where you're going. You can make adjustments in real time. You can turn left or right, speed up or slow down, and you can do it instantly. But when you're landing on the moon, everything is delayed. There's a communication delay between Earth and the moon. It takes about 1.5 seconds for a radio signal to travel from the moon to Earth. That might not sound like much, but when you're landing a spacecraft at thousands of miles per hour, 1.5 seconds is an eternity. By the time Mission Control on Earth sees what's happening and radios back instructions, the situation has already changed. This means that landing on the moon can't be controlled from Earth. The people actually landing have to make decisions in real time. They have to look at their instruments, look at the surface of the moon, and make split-second decisions about where to land and how fast to descend. Remember, they're doing this for the first time. There's no practice run. There's no second chance. They get one shot to land safely or they crash. And speaking of the surface, let's talk about what they're actually landing on. The moon's surface isn't like a parking lot. It's not flat and smooth. It's covered in craters, rocks, and dust. Lots and lots of dust. This dust is a huge problem. It's not like dust on Earth, but moon dust is created by billions of years of meteorites smashing into the surface. Each impact breaks rocks into smaller and smaller pieces. But because there's no wind or water on the moon, these pieces never get worn down and smooth. They stay sharp and jagged. Moon dust is basically made up of tiny little pieces of broken glass, and this dust gets everywhere. When a rocket engine fires near the moon's surface, it blows this dust up into clouds. But because there's no air resistance, the dust doesn't settle gently back down like it would on Earth. It shoots out in straight lines, traveling at high speeds. And it sticks to everything. It gets into equipment, into spacesuits, into machinery. And because it's so sharp, it can scratch and damage delicate instruments. Plus, when you're landing, this dust cloud can completely block your view. Imagine trying to park a car while someone is throwing handfuls of dirt at your windshield. That's what it's like trying to land through a cloud of moon dust. You can't see the surface, you can't see obstacles, and you're running out of fuel every second you spend hovering trying to find a safe spot. The Apollo 11 landing, the first time humans landed on the moon, almost ended in disaster because of this exact problem. Neil Armstrong and Buzz Aldrin were coming in for their landing, and the computer was taking them towards a crater filled with boulders. Armstrong had to take manual control and fly the lunar module sideways, looking for a safe spot, while the fuel gauge was getting lower and lower. They landed with less than 30 seconds of fuel remaining. 30 seconds. If they had spent 30 more seconds looking for a landing spot, they would have run out of fuel and crashed. And that brings us to another massive challenge: the technology. Everything that goes to the moon has to work perfectly in an environment that's absolutely hostile to machinery. On Earth, if something breaks, you can fix it. You have tools, you have spare parts, you have help nearby. But on the moon, you're completely isolated. Something breaks, you have to fix it yourself with whatever you have available. And you're doing this while wearing a bulky spacesuit with thick gloves that make it hard to grip small objects in an environment where temperatures swing from boiling hot to freezing cold. During the lunar day, when the sun is shining on the moon's surface, temperatures can reach 260 degrees Fahrenheit. That's hot enough to boil water, but during the lunar night, temperatures drop to minus 280 degrees. That's colder than anywhere on Earth, way colder than Antarctica. These extreme temperature swings create enormous stress on equipment. Materials expand when they heat up and contract when they cool down. Do this enough times and things start to crack and break. Seals fail, electronics malfunction, metal parts warp. Everything has to be designed to withstand these temperature extremes. And even then, there's always a risk that something will fail at the worst possible moment. And then there's radiation. On Earth, we're protected from space radiation by our atmosphere and by Earth's magnetic field. These act like shields, blocking most of the harmful radiation from the sun and from deep space. But the moon doesn't have either of these protections. Oh, it doesn't have an atmosphere, and it doesn't have a magnetic field. Which means anyone on the moon's surface is exposed to radiation levels that would be extremely dangerous over long periods. The Apollo astronauts could only stay on the moon for a few days at most. Any longer, and they would have been exposed to dangerous levels of radiation. This is one of the big challenges for future moon missions. If we want to establish a permanent base on the moon, we need to figure out how to protect people from radiation for months or even years at a time. Now, let's talk about getting back home, because landing on the moon is only half the challenge. You also have to launch from the moon and make it back to Earth. And launching from the moon brings its own set of problems. On Earth, when we launch rockets, we have teams of thousands of people. We have engineers monitoring every system, we have multiple redundant backups, we have launch facilities with all kinds of support equipment. But when you launch from the moon, you don't have any of that. You have a small crew, limited equipment, and if anything goes wrong, there's no emergency crew to help you. The lunar module, the spacecraft that landed on the moon, had to split in half for the return journey. The bottom half stayed on the moon as a launch pad, and the top half, which contained the crew, had to launch perfectly and rendezvous with the command module orbiting above. This rendezvous had to be precise within a few feet. If they missed, the astronauts would be stranded in orbit around the moon with no way to get home. And here's something that most people don't think about. When you launch from the moon, you're launching into the vacuum of space. There's no air resistance to worry about, which sounds like it makes things easier, but it also means there's no air to help you steer. On Earth, rockets can use fins and the air resistance to help guide them. In the vacuum of space, you can only steer by firing small rocket thrusters, and you have to be incredibly precise. Let me break down the actual sequence of what has to happen for a successful moon landing mission. First, you launch from Earth. This requires a massive rocket burning thousands of tons of fuel just to escape Earth's gravity. Then you travel for 3 days through empty space, making small course corrections along the way to ensure you're heading to the right spot. When you reach the moon, you have to slow down and enter orbit around it. This is called lunar orbit insertion, and it requires firing your rocket engines at exactly the right time for exactly the right duration. Fire too long, and you'll slow down too much and crash into the moon. Fire too short, and you'll fly right past and head off into deep space. Once you're in orbit, the landing craft separates from the main spacecraft. 2 astronauts get into the lunar module, while 1 stays in the command module, orbiting above. The lunar module fires its engines to leave orbit and begin descending to the surface. This is where everything we talked about earlier comes into play. The navigation challenges, the fuel limitations, the dust, the terrain, all of it. After landing, the astronauts have a limited time on the surface. They have to collect samples, set up experiments, and do all their planned activities before their life support runs out. Then they have to get back into the lunar module, seal it up, and prepare for launch. The launch from the moon is one of the most critical moments. The ascent engine has to fire perfectly. There's no backup engine. If it fails, the astronauts are stuck on the moon with no way to get home. Assuming the engine works, the lunar module blasts off and has to reach orbit around the moon, then carefully approach and dock with the command module. After docking, the astronauts transfer back to the command module, seal it up, and separate from the lunar module. Then they fire the command module's engines to leave lunar orbit and head back to Earth. This is another critical engine burn, too much power, and they'll come back too fast and burn up in Earth's atmosphere. Too little power, and they'll be stuck in a slow trajectory that could take weeks or months to get home. The journey back to Earth takes another 3 days, and then comes re-entry. The spacecraft has to hit Earth's atmosphere at exactly the right angle. Too steep, and the friction will generate so much heat that the spacecraft will burn up. Too shallow, and the spacecraft will skip off the atmosphere like a stone skipping on water, bouncing back into space. If everything goes right, the spacecraft slows down as it passes through the atmosphere, deploying parachutes to slow down even more, and finally splashes down in the ocean where recovery teams are waiting. But every single step of this process has to work perfectly. One malfunction, one miscalculation, one equipment failure, and the mission could end in disaster. Now let's talk about some of the specific technical challenges that make moon landing so difficult. One of the biggest is something called the rocket equation. This is a mathematical formula that describes how much fuel you need to reach a certain speed. And the problem is that as you add more fuel to go faster or farther, the rocket gets heavier, which means you need even more fuel to lift that extra weight, which makes it heavier still. This creates a situation where most of the rocket's weight is fuel. The Saturn V rocket weighed 6 million pounds at launch. The command module that returned to Earth weighed about 12,000 pounds. That means that about 99.8% of the rocket's weight was stuff that got thrown away or burned as fuel. Only 0.2% of the rocket actually made it back to Earth. Think about that for a second. To send 3 people to the moon and back, we needed a rocket that weighed as much as 400 fully loaded semi-trucks. And of all that weight, only a tiny capsule about the size of a small car actually returned. Everything else was discarded along the way. This is why every ounce matters in space travel. Engineers spend years trying to make components lighter, trying to squeeze every bit of efficiency out of the fuel, trying to reduce weight wherever possible. Because every pound you can save on the spacecraft means one less pound of fuel you need to carry, which means one less pound of fuel to lift that fuel, and so on. Another major challenge is life support. Humans need air to breathe, water to drink, and food to eat. And in space, there's none of these things. Everything has to be brought along, which adds weight. The spacecraft has to carry oxygen tanks, water tanks, food supplies, and all the equipment needed to keep the astronauts alive. But it's not just about carrying supplies. The spacecraft also has to remove carbon dioxide from the air. When we breathe, we take in oxygen and breathe out carbon dioxide. In a sealed spacecraft, this carbon dioxide builds up and can become toxic, so the spacecraft needs systems to scrub the carbon dioxide from the air and either vent it outside or convert it back into breathable oxygen. Temperature control is another life support challenge. Without an atmosphere to regulate temperature, spacecraft can get extremely hot on the side facing the sun and extremely cold on the side facing away. The spacecraft needs systems to regulate temperature, keeping the crew compartment at a comfortable level while the outside swings between extreme heat and extreme cold. And then there's the human factor. Being in space is physically demanding. Journey to the moon takes place in microgravity, where astronauts float weightlessly. This might sound fun, but it actually causes a lot of problems. Without gravity, muscles don't have to work as hard, so they start to weaken, bones start to lose density. The human body is designed to work in Earth's gravity, and when you take that gravity away, all kinds of things start to go wrong. Astronauts have to exercise regularly to keep their muscles and bones strong. But even with exercise, there's still muscle loss and bone loss over time. For short moon missions, this isn't a huge problem. But for longer missions, it becomes a serious concern. There's also the psychological challenge. Imagine being locked in a small capsule with 2 other people for over a week. You can't go outside. You can't get away. You're in constant danger, knowing that the slightest mistake could kill you. You're farther from home than any human has ever been. And you're relying on technology that has never been fully tested in these exact conditions. The stress is enormous. Astronauts have to be not just physically capable, but mentally tough. They have to be able to stay calm under pressure, make good decisions when things go wrong, and work effectively as a team even when they're exhausted and stressed. Now, if you're enjoying this breakdown and learning something new, make sure you're subscribed to the channel. We dive deep into topics like this all the time, and honestly, there's so much more to explore. Hit that subscribe button so you don't miss out. Let's talk about some of the things that can go wrong during a moon landing. Apollo 13 is probably the most famous example. The crew was on their way to the moon when an oxygen tank exploded. Suddenly, the spacecraft was losing oxygen and power. The crew had to abandon the main spacecraft and move into the lunar module, which was designed to support 2 people for 2 days on the moon's surface. Now it had to support 3 people for 4 days in space. They had to shut down almost all systems to conserve power. Temperature inside dropped to just above freezing, and they had to figure out how to get home. The spacecraft was already on a trajectory to loop around the moon, but that trajectory would have brought them back too slowly. They would have run out of oxygen before they got home, so they had to use the lunar module's descent engine to push them into a faster trajectory home. They made it back, but only barely. During Apollo 11, the landing computer was overloaded and kept giving error messages. Armstrong and Aldrin had to decide whether to abort the landing or trust that the computer would keep working. During Apollo 12, the rocket was struck by lightning during launch. Twice. These incidents show that even with the best planning, things can still go wrong. Now let's talk about why the moon landing is actually harder today than it was in the past. You might think that with modern technology it would be easier. We have better computers, better materials, better understanding of space. But in some ways, it's actually harder. The main reason is that we lost a lot of the knowledge and infrastructure from the Apollo program. The Saturn V rockets aren't made anymore. The factories that built them were closed decades ago. The engineers who designed them have retired or passed away. The detailed knowledge of how everything worked has been partially lost. Sure, we have blueprints and documentation, but there's a difference between having plans on paper and actually knowing how to build something. There were thousands of little tricks and techniques that the workers used, things that were never written down because they were just common knowledge at the time. That knowledge is gone now. If we wanted to build a Saturn V rocket today, we would essentially have to start from scratch. We'd have to rebuild the factories, retrain workers, and rediscover a lot of the manufacturing techniques. And because we'd be starting over, we probably want to update the design to use modern technology, which means redesigning everything. It would be a massive undertaking. Plus, there's the cost. The Apollo program cost about $250 billion in today's money. That's an enormous amount of money, and it was spent over about 10 years. To do something similar today would require a sustained commitment of resources and political will that's hard to achieve. Another challenge is safety standards. In the 1960s, we were willing to accept more risk. The goal was to beat the Soviet Union to the moon, and we were willing to push the boundaries of what was safe to make that happen. Today, we're much more risk-averse. We want higher safety margins, more testing, more redundancy. All of this is good for keeping astronauts safe, but it also makes missions more expensive and more time-consuming. There's the question of why we're going. During the Apollo era, there was a clear goal: beat the Soviets to the moon, demonstrate American technological superiority. Once that goal was achieved, public interest waned. Without a compelling reason to keep going to the moon, it's hard to justify the enormous expense. This brings us to the future of moon landing. There's renewed interest in going back to the moon. NASA has the Artemis program, which plans to land astronauts on the moon again. Private companies are developing their own lunar landers. There's talk of establishing a permanent base on the moon. All of these plans face the same challenges we've been discussing: the distance, the fuel requirements, the hostile environment, the radiation, the dust, the extreme temperatures. None of these problems have gone away. We have better technology than we did in the 60s, but the fundamental challenges remain the same. One thing that might make future moon landings easier is if we can use resources already on the moon. The moon has water ice in permanently shadowed craters near the poles. If we can extract this water and break it down into hydrogen and oxygen, we can use it as rocket fuel. This would mean we wouldn't have to carry all our fuel from Earth. We could refuel on the moon. The moon also has minerals and metals that could be used for construction. Instead of bringing building materials from Earth, we could potentially make them on the moon using lunar soil and rocks. This would dramatically reduce the amount of cargo we need to transport from Earth, making missions cheaper and more sustainable. But extracting and processing these resources brings its own challenges. It requires heavy equipment, power sources, and skilled workers. And all of this has to function in the harsh lunar environment. It's not impossible, but it's definitely not easy. There's also the question of where to land. The Apollo missions landed near the moon's equator, in relatively flat areas. But the most interesting resources are near the poles, where the water ice is located. Landing near the poles is more challenging because the sun is always low on the horizon, creating long shadows and making it harder to see obstacles. Plus, these areas are colder and receive less sunlight for solar power. Another consideration for future missions is reusability. The Apollo spacecraft were all single-use. Once they completed their mission, they were discarded. Modern spacecraft are being designed to be reusable, which would dramatically reduce costs. But making something reusable in the harsh environment of space is extremely challenging. Everything has to be more robust, more reliable, and easier to maintain. Let's talk about some specific numbers to really drive home how difficult moon landing is. The lunar module that landed on the moon weighed about 33,000 pounds when fully fueled. It had to slow down from a speed of about 30,600 miles per hour down to zero, all while fighting against the moon's gravity. To do this, it needed about 18,000 pounds of fuel. That means more than half its weight was fuel. And this fuel had to last for the entire descent, which took about 12 minutes. 12 minutes doesn't sound like long, but when you're burning hundreds of pounds of fuel per second, every second counts. The landing had to be timed perfectly to ensure they landed in the right spot with enough fuel remaining to hover and find a safe landing site. The margin for error was tiny. If they came in too fast, they'd crash. Too slow, and they'd run out of fuel and fall. If they used too much fuel looking for a landing spot, they wouldn't have enough to land safely, and all of this had to be done manually, with the astronauts making split-second decisions based on what they could see out the window. The computing power available to the Apollo astronauts was laughably small by today's standards. The Apollo guidance computer had about 72 kilobytes of memory. Your smartphone has millions of times more memory than that. The computer could barely do basic calculations and navigation. Everything else had to be done by the astronauts using their training and judgment. And yet, despite these limitations, they succeeded. 6 times, 6 different Apollo missions successfully landed on the moon and returned home. That's a testament to the incredible skill and bravery of the astronauts and the brilliant engineering of the people who designed and built the spacecraft. But it's also a reminder of just how difficult it is. Even with perfect planning and execution, things can go wrong. Even with the best equipment and the best people, success is never guaranteed. Every moon landing is a carefully orchestrated dance where thousands of things have to go right. And if even one of them goes wrong, the whole mission can fail. So when people ask why we don't go to the moon more often, or why it's taking so long to go back, this is why. It's not that we've forgotten how to do it, it's that doing it safely and successfully requires an enormous effort. It requires developing new technology, training people, building infrastructure, and accepting significant risk. The moon is a harsh and unforgiving place. There's no air, no water, no shelter. The temperature swings are extreme, the radiation is dangerous, the dust is abrasive and gets into everything, and it's 250,000 miles away from any help. Landing on the moon requires solving dozens of technical challenges simultaneously. You have to navigate precisely across vast distances. You have to carry enough fuel for the entire journey while keeping the spacecraft light enough to launch. You have to protect the crew from radiation and temperature extremes. You have to land safely on uncertain terrain while running out of fuel. You have to launch from the surface with no support infrastructure. And you have to do all of this knowing that if anything goes wrong, there's no backup plan, no rescue mission, no way home. This is why moon landing is so difficult. It's not one big problem, it's hundreds of smaller problems, all interconnected, all critical. Solve 99 of them and miss just one, and the mission fails. Every system has to work perfectly. Every calculation has to be correct. Every decision has to be the right one. And despite all these challenges, we've done it. Humans have walked on the moon. We've stood on the surface of another world, looked back at Earth hanging in the black sky, and returned to tell the tale. It's one of humanity's greatest achievements precisely because it's so difficult. The fact that we accomplished moon landings in the 1960s and 70s with primitive technology compared to what we have now is incredible. It shows what humans are capable of when we set our minds to something and commit the resources needed to achieve it. But it also shows why we can't take it for granted. Each moon landing was a miracle of engineering and human skill. The fact that all the astronauts came home safely was not guaranteed. They knew the risks. They trained for years. They prepared for every possible scenario, and even then, luck played a role. Looking forward, as we plan new missions to the moon, we carry this knowledge with us. We know how hard it is. We know what can go wrong. We know the challenges we face. And hopefully, this knowledge will help us do it better, safer, and more sustainably in the future. The moon isn't impossible to reach. We've proven that. But it's not easy either. It requires the best of human ingenuity, courage, and determination. It requires pushing the boundaries of what's possible and accepting that failure is always a possibility. Every successful moon landing is a victory against enormous odds. Every astronaut who sets foot on the lunar surface is doing something that defies the natural order, that challenges what we thought was possible. And that's what makes it so remarkable. Not just that we can do it, but that it's so incredibly difficult that doing it represents one of the pinnacles of human achievement. The moon is close enough to see with our eyes, but far enough away that reaching it requires everything we have. It's a reminder of both how far we've come and how much farther we still have to go. So the next time someone talks casually about going to the moon, remember everything we've discussed. Remember the distance, the fuel, the navigation, the hostile environment, the radiation, the dust, the temperature extremes, the technology requirements, the human factors, the risks. Remember that every moon landing is an incredible feat that requires thousands of people working together, years of preparation, enormous resources, and more than a little bit of luck. The moon is waiting for us. It's been waiting for billions of years, and it will keep waiting, patient and unchanging, while we figure out how to return safely and sustainably. Because as difficult as it is to land on the moon, the dream of doing it again, of establishing a permanent human presence on another world, is worth every challenge we face. Now let's dive deeper into some specific aspects that really highlight why this is so challenging. Let's talk about the actual physics of what happens when you try to land on the moon. When you're descending to the moon's surface, you're fighting against gravity the entire way down. The moon's gravity is about 1/6 of Earth's gravity, which sounds like it would make things easier, and in some ways it does. But it also creates unique challenges that don't exist on Earth. With weaker gravity, objects fall more slowly. On Earth, if you drop something, it accelerates at 32 feet per second squared. On the moon, it's only about 5 feet per second squared. This means you have more time to react when something starts to go wrong. But it also means that your rocket exhaust behaves differently. When you fire a rocket engine on the moon, the exhaust gases spread out more than they would on Earth. They didn't get pulled down as quickly by gravity, so they form this expanding cloud that can interfere with your sensors and visibility. This is on top of the dust problem we already talked about. The combination of exhaust gases and dust creates a situation where you're essentially flying blind for the final moments of landing. And here's another thing. The moon's gravity isn't uniform. The moon has what are called mass concentrations, or mass cons. These are areas where the density of rock beneath the surface is higher, creating slightly stronger gravitational pull. When you're orbiting the moon or descending to the surface, these mass cons can pull your spacecraft slightly off course. The Apollo astronauts had to account for these gravitational anomalies in their descent planning. If they didn't, they could end up miles away from their intended landing site. And remember, they only had enough fuel for one landing attempt. If they missed their target, they couldn't just circle around and try again like you would when landing an airplane. Now let's talk about the actual landing sequence in more detail, because it's fascinating how complex it is. The lunar module starts its descent from an orbit about 60 miles above the moon's surface. It fires its descent engine to slow down and drop out of orbit. As it descends, the spacecraft is tilted backwards so the engine can slow its forward motion while also fighting against the moon's gravity. The crew is lying on their backs, looking up at the stars, trusting their instruments because they can't see where they're going yet. About 6 minutes into the descent, the spacecraft pitches forward so the crew can see the surface for the first time. They're still traveling at hundreds of miles per hour. The computer is guiding them toward their planned landing site, but the crew is watching, ready to take over if they see any problems. At about 500 feet, the spacecraft pitches up so the crew has a clear view of the landing site. They're looking for obstacles, for safe spots to land. The commander has his hand on the control stick, ready to take manual control if needed. And then, in the final 100 feet, they're moving almost straight down, with the engine fighting against gravity. Looking for the perfect spot, avoiding craters and boulders. In the last few seconds, they're hovering just a few feet above the surface, kicking up massive clouds of dust, burning fuel at an alarming rate. And then, contact. The landing probes touch the surface, the crew shuts down the engine, and they settle onto the moon. The entire descent takes about 12 minutes, from start to finish. 12 minutes where everything has to work perfectly. Now let's talk about what happens after landing. I think the hard part is over, but there are still huge challenges to deal with. The first is making sure the spacecraft is stable. The moon's surface isn't perfectly level. If one leg of the lunar module ends up on a rock or in a small crater, the whole spacecraft could be tilted at a dangerous angle. The Apollo 14 landing was particularly nerve-wracking because the spacecraft landed on a slope. It was tilted at an 8-degree angle, which doesn't sound like much, but it was close to the maximum safe tilt angle. If the spacecraft had been tilted anymore, it might have tipped over when the crew tried to launch. Discussed aborting the surface activities and launching immediately, but ultimately decided the tilt was safe enough to continue the mission. Then there's the issue of thermal management. On the moon, there's no air to conduct heat away from the spacecraft. Everything heats up through radiation from the sun and cools down through radiation into space. The spacecraft has to have systems to control this temperature, keeping the crew comfortable and the equipment functioning. The spacesuits the astronauts wear when they go outside face the same challenge. On the side facing the sun, temperatures can be over 200 degrees. On the side facing away from the sun, temperatures can be below zero. The suit has to protect the astronaut from both extremes simultaneously. The suits do this using layers of insulation and a cooling system that circulates water through tubes sewn into the undergarment. The water absorbs heat from the astronaut's body and then radiates it away through the suit's outer layers. It's an elegant solution, but it adds weight and complexity to the suit, and if the cooling system fails, the astronaut can overheat within minutes. Walking on the moon in these suits is also much harder than it looks. The suits are pressurized, which makes them stiff and resistant to movement. Bending your arms or legs requires effort. The thick gloves make it hard to grip objects, and because of the moon's lower gravity, moving around requires learning a whole new way of walking. The Apollo astronauts found that hopping was often easier than walking. There's also the constant danger of falling. If an astronaut falls on the moon and damages their suit, it could be fatal. A tear in the suit would cause rapid decompression. This is why every movement on the moon has to be careful and deliberate. Let's talk about the experiments and work the astronauts do on the surface. It's not just about walking around and planting a flag. Every moon mission has scientific objectives. The astronauts collect rock samples, set up instruments, conduct experiments. All of this has to be done while wearing thick gloves in a bulky suit with limited time. Collecting rock samples sounds simple, but on the moon it's challenging. The rocks are often embedded in the lunar soil. The astronauts use tools like hammers and core tubes to extract samples, but the tools have to be specially designed. And because the astronauts are wearing pressurized gloves, they can't feel what they're doing. The instruments they set up have to survive for months or years on the moon's surface after the astronauts leave. They have to withstand the temperature swings, the radiation, the micrometeorite impacts. Some of these instruments are still working decades after they were deployed. Now let's talk about one of the most overlooked challenges, the psychological toll. Being on the moon is isolating in a way that's hard to describe. You're standing on the surface of another world, looking up at Earth hanging in the black sky. You're 240,000 miles from home. If something goes wrong, there's no rescue coming. The pressure is immense. You know that millions of people are watching back on Earth. You know that any mistake could end the mission, or worse, end your life. You have a limited amount of time to complete your objectives, and you're doing all of this while exhausted. The Apollo astronauts talked about how surreal it felt to be on the moon. The sky is black even during the day because there's no atmosphere to scatter light. The shadows are pitch black. Everything is stark contrasts, bright whites and deep blacks. It's a landscape unlike anything on our planet. After completing their surface activities, the astronauts have to get back into the lunar module, seal it up, and prepare for launch. This is another critical moment. They have to make sure they've collected all the samples they need. They have to stow all their equipment properly. They have to check that their spacesuits didn't get damaged during the surface activities. Then they have to repressurize the lunar module. It'd been in vacuum for hours. And now they're bringing that vacuum inside with them in the form of moon dust on their suits. When they repressurize, this dust starts floating around the cabin. It smells strange, described by astronauts as smelling like spent gunpowder. And it's everywhere. This dust is a contamination hazard. If it gets into seals or valves, it can cause leaks. If it gets into the astronaut's eyes or lungs, it can cause irritation. It's an unavoidable consequence of working on the lunar surface, but it's something that has to be managed carefully. Launch from the moon is the point of no return. Once that ascent engine fires, there's no going back. It has to work. There's no backup. There's no abort option. If the engine fails, the astronauts are stranded on the moon with no way to get home. The engine fires, and the upper stage of the lunar module blasts off, leaving the lower stage behind as a launch platform. The crew is pushed back in their seats by the acceleration. They watch through the window as the lunar surface drops away. They're heading back to orbit, back to the command module, back toward home, but they're not safe yet. They have to reach orbit at the right speed and the right altitude. Then they have to locate the command module and carefully approach it. Rendezvous and docking is another nerve-wracking procedure. The lunar module has to approach the command module slowly and carefully. line up perfectly and gently dock, creating an airtight seal between the two spacecraft. Only after they've docked, transferred back to the command module, and safely separated from the lunar module can they truly relax. Even then, they still have to make the journey home, re-enter Earth's atmosphere, and splash down safely. Every single one of these steps is fraught with challenges and risks. Every step requires precision, skill, and a bit of luck. The fact that we successfully completed 6 moon landing missions without losing any astronauts on the lunar surface is remarkable. Of course, we did lose astronauts. The Apollo 1 crew died in a fire during a ground test. We came close to losing the Apollo 13 crew. This danger, this difficulty, is exactly why moon landings are so significant. They represent humanity pushing the boundaries of what's possible. They show what we can accomplish when we commit ourselves fully to a goal. As we look toward future moon missions, we face many of the same challenges that the Apollo astronauts faced: distance, fuel, environment, radiation. But we also have advantages they didn't have: better computers, better materials, better understanding of the moon. We can build on their experiences and hopefully make the journey safer and more sustainable. The goal now isn't just to visit the moon and come home, it's to establish a lasting presence there, to build habitats where people can live for months at a time, to set up research stations and maybe even extract resources that can support further exploration. Every one of these goals brings new challenges. Building structures on the moon means dealing with the dust, the temperature swings, the radiation, all while working in bulky suits with limited time and resources. These are all solvable problems, but none of them are easy. Each one requires innovation, testing, and investment. The challenges we face in returning to the moon are driving innovation in engineering, material science, robotics, and medicine. The solutions we develop for moon habitation could have applications here on Earth. And the knowledge we gain from living on the moon will help us when we eventually try to send humans even farther, to Mars and beyond. The moon is our first step into the solar system. It's close enough that we can reach it with current technology, but far enough that it forces us to solve real problems about living away from Earth. Every challenge we overcome on the moon brings us closer to becoming a truly spacefaring species. So when we ask why it's so difficult to land on the moon, the answer is that it's difficult because it's extraordinary. It's pushing against the natural limits of what humans and our technology can achieve. It's leaving the protection of Earth's atmosphere and gravity to venture into an environment that's actively hostile to human life. It's traveling vast distances with no margin for error. The difficulty is the point, because in overcoming that difficulty, we prove that humans can do remarkable things. We show that with enough determination, enough ingenuity, and enough cooperation, we can achieve what seems impossible. We demonstrate that the universe is not beyond our reach. That's why the challenge of landing on the moon matters. Not just for the scientific knowledge we gain or the technologies we develop, but for what it says about human potential. We can reach the moon. We have reached the moon. And one day, we'll go back to stay.